There's a telescope sitting in a valley in Chile called Rio Hurtado, and most nights it does something fairly unglamorous. It sweeps back and forth across the sky, automatically without anyone watching, looking for rocks that might one day be a problem for us. That's the entire job. It's a smoke alarm with a mirror in it. And on the 1st of July 2025, it found something that was never ours. That's what tonight is about. A comet called 3I Atlas, which came in from between the stars, went round our sun and left again, and in the process handed us the oldest chemistry anybody has ever measured. I've been reading about this thing for the better part of a year now, and I'll tell you the honest version up front. Nothing frightening happened. Nobody panicked. There's no twist waiting at the end of this video, and I'm not going to pretend there is. What there is a very long, very cold story about a piece of a dead star system and the slightly absurd number of machines we pointed at it. If you like this sort of thing, subscribing helps. That's the last I'll mention it. Let's start with the night it showed up. So, Atlas. The name is one of those acronyms that somebody clearly worked backwards from, because it stands for the Asteroid Terrestrial Impact Last Alert System, and you can practically hear the meeting where they landed on that. It's a NASA-funded survey, and it isn't one telescope, it's 4. 2 in Hawaii, 1 in Chile, 1 in South Africa, spread out around the planet so that between them they can see most of the sky most of the time, and so that when it's cloudy in one place it probably isn't cloudy in the others. What they do is not complicated conceptually. Each telescope photographs a patch of sky. Then, a bit later that night, it photographs the same patch again. Then again. And software compares the images and asks a very simple question. Did anything move? The stars won't have. Stars are, for these purposes, nailed down. Anything that shifts between one frame and the next is close to us. A satellite, an asteroid, a comet, a bit of space junk, and the software flags it and hands it to a human. That's the whole system. It's a difference engine. It doesn't know what anything is. It only knows what moved. The point of building it was defensive. Atlas exists because we would quite like some warning if a decent-sized rock is heading our way, and the last alert bit of the name is doing a lot of quiet work there. It's not designed to find things decades out. It's designed to catch the ones that would otherwise arrive unannounced. Weeks of notice rather than none. It is, in the most literal sense, a burglar alarm for the inner solar system. And on the 1st of July 2025, the Chilean unit flagged a moving dot and passed it along, and it went into the system under the name A11PL3Z, which is the kind of provisional designation that gets handed out to a few thousand things a year, and means absolutely nothing. It's a filing reference. It's the astronomical equivalent of a ticket number at a deli counter. The report went to the Minor Planet Center, which is where all of this ends up. Every survey, every observatory, every amateur with a good camera and a steady mount, it all funnels into the same place, and the Minor Planet Center's job is to work out whether the dot you just found is a new dot, or a dot somebody already found in 1998. Most of the time, it's the second one. There's a lot of gravel out there, and we've catalogued a fair chunk of it. This one was a new dot. Now, here's the bit I actually find lovely about this story, and it's got nothing to do with telescopes. Once you've got a new object and a rough idea of where it's going, you can run the maths backwards and work out where it must have been. And then you go and look, not at the sky, at the filing cabinet. Every survey telescope in the world is generating enormous quantities of images every single night. And almost all of those images contain things nobody has ever noticed, because nobody was looking there for that. The data's just sitting on a hard drive, quietly, being unexamined. So they went digging, and they found it. Pre-discovery images, pre-coveries, which is a nicely odd little word, turned up in the Atlas archives going back to the 14th of June 2025. 2.5 weeks before anyone knew it existed, 3 different Atlas telescopes around the world had already photographed it. So had Caltech's Zwicky Transient Facility at Palomar. It was there, in the frames, as a faint smudge that nothing and nobody had reason to look twice at. And then it got better. Someone went and checked TESS. TESS is the Transiting Exoplanet Survey satellite, and it has nothing whatsoever to do with comets. Its entire purpose is to stare at stars and watch for the microscopic dimming that happens when a planet crosses in front of one. It's a planet hunter. But to do that job it needs an enormous field of view, because it's got to watch a lot of stars at once, and an enormous field of view means it is constantly and accidentally photographing everything else in the frame. TESS had it. From May 2025. 55 days before the discovery. I love that. 55 days. A planet-hunting satellite with no interest in the inner solar system had been sitting on the first images of the third interstellar object ever found, filed away, for nearly 2 months, and the only reason we know is that somebody thought to look. Those observations turned out to be genuinely useful too. The longer you can trace an object's path, the better you can pin down where it's going and where it came from, and Tess handed the team an extra 8 weeks of track for free. There's an amateur astronomer called Sam Dean who dug up even more of these, going back through late June, and who also worked out why nobody had spotted it sooner. And the reason is almost funny. It had been passing in front of the galactic centre. The galactic centre is the direction you look when you look toward the middle of the Milky Way, and it is absolutely stuffed with stars. It's the busiest part of the sky. So if you're a piece of software whose one skill is noticing that a dot has moved against a background of stationary dots, and the dot in question is drifting through a region that has approximately 11 billion background dots in it, you are going to have a bad time. It was camouflaged, not by anything clever, just by traffic. I keep coming back to that, because it slightly undercuts the whole idea of discovery as an event. We didn't discover this thing on the 1st of July. We noticed it on the 1st of July. It had been in our possession, in our data, on our disks for weeks. And depending on how you count, it had been passing through our solar system for considerably longer than that without a single human being having any idea. Anyway, the naming. Comets are generally named after whoever found them, which is why the historical record is full of things like Hale-Bopp and Shoemaker-Levy and Hyakutake, and which is also why a great many amateur astronomers have spent a great many cold nights hoping. But when a machine finds it, the machine gets the name. So, Atlas. The 3i is the interesting half. The I is for interstellar. This thing came from outside our solar system, and we'll get into how we knew that shortly, because the answer is a single number and it's quite a satisfying one. And the 3 is because it's the third. That's it. That's the whole naming scheme. There's no committee, no Latin, no mythology. It's the third one we've caught, so it's number 3, and if we catch a fourth it'll be 4i, and if we catch a 40th it'll be 40i. It's also got a second name which nobody uses and which I think deserves a mention. It's officially C2025N1 as well. That's the standard comet designation, C for a non-periodic comet, 2025 for the year, and then N1, which encodes the half month it was found in, and the fact that it was the first one that fortnight. So it's got a formal comet name and an interstellar name, running in parallel, and everyone ignores the Comet 1 because 3i Atlas sounds better, and because the interstellar bit is the whole point. But the fact that it has a comet designation at all is a little fossil of the confusion at the start. Because for the first day or so, nobody was certain it was a comet. The early observations couldn't tell. It might have been an asteroid, a bare rock, an Oumuamua-type object, and the difference matters enormously, because a rock tells you almost nothing, and a comet tells you everything. A rock is a closed box. A comet opens itself up and shows you its contents for free, which tells you something about how new all of this is. We have a naming convention for interstellar objects that is essentially just counting on our fingers, because we have never had enough of them to need anything more sophisticated. Compare that to asteroid designations, which are a baroque nightmare of letters and cycles and half months, because we've found well over 1 million of the things, and had to invent a system that could cope. 3. We're on 3. So that's the 1st of July 2025. A smoke alarm in a Chilean valley notices a smudge. The smudge goes into a database under a meaningless code. Somebody runs the numbers, somebody else goes rummaging through the archives, and within a few days it becomes clear that a machine built to warn us about local rocks has, entirely by accident, caught something from another star. And everything moved very quickly after that, which academia is not famous for. At Michigan State, an astronomer called Darrell Seligman heard something about an object before he went to bed, at which point there wasn't much information to go on, and by the time the dust settled he was leading the first scientific paper on the thing, written, essentially, in a scramble, with an international team in the days immediately after. That's not how papers normally go. Papers normally take a year and involve at least one argument about author order, but there was a clock running, and everyone could see it. And the thing that made everyone sit up wasn't the picture. The picture is, I have to be honest, not much. It's a smear. Every early image of this thing is a smear, and if you go and look at the discovery frames expecting drama, you will be let down. It was the arithmetic. The number is 6.14. That's it. That's the whole case. Everything else about this object, the age, the chemistry, the dead star, all of it, hangs off one measurement, and the measurement is eccentricity, and the value came out at 6.14 to 135, give or take about 2 parts in 100,000. Let me explain what that means slowly, because it's genuinely one of the more elegant ideas in astronomy, and it gets explained badly a lot. Eccentricity is a description of shape, specifically the shape of the path something traces when it moves under gravity. And there are only a handful of shapes available. That's the surprising part, honestly. You'd think a thing falling around a star could carve out any old squiggle it fancied, but it can't. Gravity is fussy. You get a circle, an ellipse, a parabola, or a hyperbola, and nothing else. Ever. Eccentricity 0 is a perfect circle. Nothing in real life is a perfect circle, but it's the reference point. Earth's eccentricity is about 0.07, which is a circle that's had a very gentle sit on. Mars is 0.09. Pluto, which is famously a bit of a nonconformist, is around 125, and you can see that in the diagrams, its orbit is visibly squashed. It crosses inside Neptune's for a couple of decades at a time, and it looks wrong in a way that Earth's doesn't. Comets from our own neighbourhood go much further. A long-period comet might be 0.99, 0.995, something like that. Those are enormous stretched ovals. The comet spends almost all of its existence out in the cold dark doing nothing, then falls inward, whips round the sun in a matter of months, and goes back out for another few thousand years. Halley's is about 0.967. That's an object on a very long leash, but it is on a leash, and that's the key. Anything below 1 is bound. It's ours. It might take 10,000 years to come back, but it is coming back, because it never had enough speed to get away, and the sun's gravity has it by the collar. At exactly 1, the leash goes slack. That's a parabola, and it's the mathematical borderline, precisely enough energy to escape, arriving at infinity with exactly 0 speed left over. It's a theoretical fence post. Nothing sits on it, because sitting exactly on it would require a coincidence to about 15 decimal places. Above 1, you're free. That's a hyperbola. You come in, you bend around the star, and you leave, and you never come back. And the higher the number, the less the star managed to bend you at all. 6.14. I want to sit on that for a second, because the size of that number is doing something people tend to skip past. It isn't marginally over the line. It isn't 1.001, where you'd squint at the error bars and wonder whether a bit of outgassing had nudged it. Something at 1.05 might be a homegrown comet that got flung by Jupiter on the way out and technically achieved escape velocity. That happens. That's a local story. You do not get there by accident. There is no gravitational arrangement inside our solar system that can produce that. Jupiter couldn't do it if Jupiter spent a century trying. To be on a path that's steeply hyperbolic, you have to have arrived already moving, from outside, carrying speed that was never ours to give you. And it's worth setting it against the other two because all three are hyperbolic, and they are not remotely alike. Oumuamua came in at about 1.2, which is over the line, decisively, not arguably, but it's close to the line. It was moving at roughly 26 kilometers per second relative to the Sun before it got here, which is, by the standards of things drifting between stars, positively sedate. There's a whole line of thinking that Oumuamua's speed matched the average motion of the local stars so well that it might have been drifting more or less with the neighbourhood for a very long time, rather than being flung across it. A tourist who lives nearby, Borisov was about 3.4. Faster, further over, clearly a proper outsider, and this one is nearly double Borisov. It is by a wide margin the fastest of the three, and that isn't a small detail, because speed, in this business, is a proxy for age. Objects drifting in the galaxy get gravitationally nudged over time by everything they pass, and those nudges accumulate, and the population as a whole gets stirred and heated up. So the fast ones tend to be the ones that have been out there the longest, getting kicked around the longest. Speed is a rough odometer, which meant that before anyone had measured a single molecule, before any of the chemistry we'll get to, the orbit alone was already whispering that this thing was old. The other way to say it is the velocity at infinity, which astronomers write as v infinity, and which is my favourite bit of jargon in this whole story because of how casually enormous it is. It means Once this thing is far enough away from the Sun that the Sun no longer matters, how fast is it still going? For a bound object, the answer is 0 by definition. It doesn't get to infinity, that's the point. For 3I Atlas, the answer is about 58 kilometers per second. 58 kilometers per second left over. After the Sun has done everything it can, that's the speed it had before it got here, and it's the speed it'll have after we're a rounding error behind it. For context, Earth orbits at about 30 kilometers per second. This thing's residual, its spare change, its couldn't be bothered speed, is nearly twice the entire orbital velocity of our planet. One thing I want to correct while we're here, because it got mangled a lot in the coverage and it still gets repeated. This thing did not dive into the Sun. It didn't skim past Mercury, it didn't graze the corona, it didn't do anything of the sort. Its closest approach to the Sun was 1.36 astronomical units, which is further out than we are. It never came inside Earth's orbit. It came in, crossed Mars's orbit, turned round somewhere between Mars and us, and went back the way it came. Which is part of why the heating story turned out the way it did. It never got properly cooked. It got a warm afternoon, at a distance where our own comets are only just starting to wake up, and that was the entirety of its exposure to a star after 10 billion years of not having one. At its closest to the Sun, it was doing 68.3 kilometers per second, because the Sun had spent a while pulling on it and got some grudging cooperation out of it on the way down. Then it went round the corner and gave every bit of that back on the way out, which is precisely what the math says has to happen, and which is still slightly annoying to think about. The Sun took a swing at it and missed. And then there's the direction, which I don't think gets enough attention. The solar system is flat. Not perfectly, but broadly. The planets all orbit in roughly the same plane, going roughly the same way, because they all condensed out of the same spinning disk 4.5 billion years ago, and spinning disks have a strong opinion about which way is round. If you built a scale model, you'd build it on a tabletop. Everything is on the tabletop. 3I Atlas came in at an inclination of about 175 degrees. 180 degrees would mean perfectly flat and perfectly backwards, so 175 is almost on the tabletop, within about 5 degrees of it, but running the wrong way round, retrograde, against the traffic in the traffic's own lane, which sounds spooky and isn't particularly. If you're coming in from a random direction with no relationship to our disk whatsoever, you can arrive at any angle, and some fraction of arbitrary angles will happen to be close to our plane. Somebody had to draw that card. This one did, and some people have made rather a lot of that, and we'll deal with all of that properly later on because there's a whole conversation to be had and it deserves better than a throwaway line here. But the retrograde bit does have a practical consequence, and it's the reason this object was moving so fast relative to us. It wasn't just going quickly, it was going quickly at us, while we were going quickly at it. 2 cars at 60 miles an hour is a very different afternoon depending on whether they're side by side or nose to nose. The closing speeds involved were absurd, and that's part of why the observing campaign had the character it did. Everything had to be arranged in advance because there was no going back for a second look. So, an orbit that could only have come from outside, a residual speed nearly twice our planet's own, and a path that bends but never closes. That was known within days, before anyone had a spectrum, before anyone knew what it was made of, before the word methane entered the conversation. The orbit had already answered the only question that really mattered. This thing was not from here. It had never been from here. It came in from the dark. It was going to leave into the dark, and everything else we were ever going to learn about it had to be learned in the window while it was passing through, which is a fairly motivating thing to tell a room full of astronomers. Now, before we get to what they did with that window, let's talk about the other two. Because 3 Atlas didn't arrive into an empty category. It arrived third, and the first two had already set some expectations, and it broke both of them in opposite directions. Oumuamua turned up in October 2017, and it has never really gone away. Picture something small and dark and reddish, tumbling, not spinning tidally like a planet, tumbling end over end the way a hammer thrown across a garden goes. It was found by Pan-STARRS in Hawaii, which is where the name comes from. It's Hawaiian, and the rough sense of it is a scout or a messenger, something that arrived first and came from a long way off. Best name in the catalogue, no contest. The trouble with Oumuamua was that it was already leaving when we found it. We caught it on the way out, weeks after it had rounded the Sun, and it was small and it was fading, and we had a matter of days. Nobody got a decent spectrum. Nobody got a decent picture. And I want to be very clear about this, because the internet is full of gorgeous renderings of a smooth grey cigar-shaped rock tumbling against the stars, and every single one of them is an artist's impression. We never resolved it. It was a point of light. The shape came from watching its brightness go up and down as it tumbled, and working backwards and concluding that it had to be very elongated to vary that much, which is real science. But it is not a photograph, and it didn't have a coma. That's the thing that made it strange. Comets, when they get near a star, produce a fuzzy cloud of gas and dust as their ice warms up and boils off. That's what a comet is. That's the definition, and it's where the tail comes from. Oumuamua had none of that. It looked like a rock, except it accelerated. Not much. A tiny push, away from the sun, over and above what gravity alone said should happen, and that's normally the calling card of a comet. The gas boiling off one side acts like a very feeble thruster and shoves the thing around slightly. But if there's no visible outgassing, and it accelerates anyway, then you have a rock that's being pushed by nothing, and that is the sort of sentence that starts arguments. The arguments have been going for 9 years now. Hydrogen ice, nitrogen ice, chipped off some distant Pluto-like world. A dust bunny, genuinely, a proposal that it was an incredibly fluffy low-density fractal aggregate that solar radiation could push around like a crisp packet in a car park, and, from Avi Loeb at Harvard, the suggestion that it might have been a light sail, which is to say, a piece of technology. That's a proper scientific position, argued in the literature, and it is also very much a minority one, and we'll come back to Loeb later because he has a lot to say about tonight's object too. The honest summary of Oumuamua is, we don't know, we're not going to know, and it's gone, which I find genuinely maddening, and I say that as someone who is normally quite relaxed about unanswered questions. Then Borisov, 2019, and Borisov was, bless it, boring. I mean that affectionately. Gennady Borisov found it, an amateur working with a telescope he'd built himself, which is a detail I refuse to skip past. Not a survey, not a machine. A bloke with a homemade telescope beat every automated system on the planet to the second interstellar object ever found. It was obviously a comet. Coma, tail, the works. It had gas, and we could measure the gas, and when we measured the gas it looked fine, familiar. There was more carbon monoxide than you'd expect, which suggested it had formed somewhere properly cold, and that was interesting. But broadly it slotted into the range of things we already knew. If you'd handed a spectroscopist the data without telling them where it came from, they'd have said comet and gone back to their lunch, which was, in its own way, a genuinely significant result. 2 data points, and they could not have been more different. One an inscrutable, tumbling non-comet that nobody can explain, and one a completely legible ordinary comet from another star. The category interstellar object turned out to have no character at all. It was just a postcode. Borisov did have one moment of drama, mind. In early 2020, on its way out, it broke. Fragmented, the nucleus threw off a chunk and for a little while there were 2 of it. Which happens to our comets all the time. They're fragile, loosely packed things, and the stress of getting warm and spinning and losing mass unevenly is enough to snap them. But it was a useful reminder that these objects are not durable. They're held together by very little. So that's the expectation 3I Atlas arrived into. One weird one, one normal one, and no idea which way the third would fall. It fell in the middle, and then wandered off in a third direction entirely. It was active from day 2, the 2nd of July 2025, David Jewett and Jane Liu on the Nordic Optical Telescope, and there it was, fuzzy, surrounded. It had a coma before it had a proper name, so straight away, not an Oumuamua situation. This was a comet unambiguously, and we'd caught it inbound months from perihelion, with everything still ahead of it. That alone was the win. That was the thing Oumuamua never gave us. Time. And it was red. Reddish. Similar to what you see in D-type asteroids, and similar to Borisov. That colour is a sign of organic compounds sitting on the surface getting hammered by radiation for a very long time, which slowly cooks them into darker, redder tars. It's a suntan, essentially, except the sun in question is the entire galaxy, and the exposure ran for billions of years. But here's the bit I want to put on the record, because at the time the coverage got away from itself somewhat. The early activity was not dramatic. Time series photometry through July 2025 put the dust production somewhere between 0.3 and 4.2 kilograms per second. That is a rate consistent with a weakly active comet a long way from the Sun, It's a garden hose. Meanwhile, the headlines were doing the thing headlines do, and the word erupting was already in circulation, and it was not at that point erupting. It was gently steaming. It hadn't even grown a visible tail yet, partly because it wasn't producing much dust, and partly because of the viewing geometry, which is to say we were looking at it from an angle where any tail it did have was pointing more or less directly away from us, and therefore hiding behind itself. The same run of observations gave the first proper handle on how it was spinning, 16 hours, plus or minus about a minute, with the brightness swinging by roughly 0.3 magnitudes as it turned, and then that swing started to shrink, down towards 0.2, not because the rotation changed, but because the coma was thickening and starting to smother the signal. You're trying to watch a lighthouse through fog that the lighthouse itself is producing. The size took much longer to pin down, and it's a good illustration of how hard this is. Early on, Hubble could only say the nucleus was somewhere between about 440 meters and 5.6 kilometers across, which is a range so wide it's almost an insult. It's the difference between a village and a small city. The reason is that you can't see the nucleus. You never can. It's buried inside its own coma, and all you're getting is the total brightness of the whole fuzzy mess, and working out how much of that light is coming off the solid bit in the middle is a nightmare. It took until after perihelion, with more Hubble data and a lot of careful subtraction, to narrow it to an effective diameter of about 2.6 kilometers, give or take 400 meters, which is a proper comet. Not a monster, not a mountain, but comfortably more massive than Borisov was. And that mass matters later, because it's one of the things people have argued about. I like that spin figure a lot though, because it's one of the few genuinely solid physical numbers we ever got out of this object. Much of what follows is inference. Clever inference, careful inference, but inference. The spin is just a measurement. It turned once every 16 and a bit hours, and that's that. So the early picture, a modestly active, reddish, slow-turning comet from another star, doing nothing especially outrageous, on a trajectory that meant it would be gone within about 18 months, and would never, under any circumstances, come back. Which is when the astronomy community did something I think is quietly remarkable. Since we're on the subject of overshooting, the response absolutely did overshoot, and it was completely correct to. Here's the situation astronomers found themselves in July 2025. There is an object in the solar system that came from another star. It will be here for about a year and a half. It will pass close to the Sun in late October, disappear behind it for a while, come back out, swing past Earth in December at a comfortable distance, cross Jupiter's orbit in the spring, and then leave forever. Not leave and return in 76 years. Leave. Every observation anybody wants ever of this specific object must be taken inside that window. There is no second season. There is no coming back to it when the funding lands or when the instrument gets fixed or when someone finishes their PhD and has time. Whatever you get, and then it's gone for the rest of the species' existence. So they went a bit mad, and honestly, good. The first stop was Mars, on the 3rd of October 2025, at about 29 million kilometers, which sounds like a lot and is in this context extremely close, a great deal closer than it ever came to us. And we happen to have quite a lot of hardware at Mars. Actually, let me put that 29 million kilometers in perspective, because it's the closest this thing ever came to anything we own. The orbits of 3I, Atlas and Mars, at their nearest points, come within about 0.018 astronomical units of each other. That's under 3 million kilometers. The two paths very nearly cross. It's just that the comet and the planet weren't at that spot at the same moment, so the actual encounter was 10 times wider than the paths themselves, which is, in orbital terms, a fairly narrow miss. It came roughly 10 times closer to Mars than it ever came to us. Nobody planned that, obviously. It's just where it went, but it meant that the best placed observers in the solar system, for the most interesting part of the approach, were on another planet. The Mars Reconnaissance Orbiter looked. MAVEN looked. Europe's Mars Express looked, and so did the ExoMars Trace Gas Orbiter, which is a spacecraft whose entire purpose is sniffing the Martian atmosphere for whiffs of methane, and which found itself pressed into service as a comet watcher because it happened to be parked in the right place. Its observations were good enough to help tighten up the comet's trajectory, which I find slightly funny, an atmospheric sniffer doing orbital mechanics as a side hustle. And then there's Perseverance. Perseverance is a rover. It's on the ground, on Mars, in a place called Jezero Crater, And its job, its one big expensive job, is to look for signs of ancient microbial life in a dried-up river delta. That's what it's for. That's why it's there. It's been methodically working through that assignment for years, drilling cores, caching samples, taking its time. And for a little while, in October 2025, it stopped, tilted its head back, and used its Mars camera to photograph a comet from another star. I have to be honest, when I first read that, I had to put my phone down for a minute. Think about what's actually in that sentence. A machine we built sitting on the surface of a different planet, looking up through a different sky, at an object that has been travelling between stars for longer than our sun has existed, and taking its picture. And the machine wasn't even designed for that. It's a geologist. It was doing a favour. That image is not good, by the way. I want to manage expectations. It's a faint smudge on a grainy frame taken by a camera at the wrong end of its capabilities, pointed at a target it was never meant to see. Astronomically, it's nearly worthless. But as an object, as a thing that exists, I'm not sure there's a better photograph in the archive. Then it went round the sun on the 29th of October and vanished from view for a bit, which is the frustrating part of the whole affair. The moment it was hottest, the moment the most interesting things were happening to its ices, it was on the far side of the sun with the glare in our eyes. There's nothing to be done about that. Geometry doesn't negotiate. It came back into view in early November and everyone got back to work, and then the fleet properly assembled. Parker Solar Probe watched it. Parker being the spacecraft that flies through the sun's outer atmosphere for a living, which gives it a rather unusual vantage point on things near the sun. Punch watched it. Punch is a set of small spacecraft designed to image the solar wind, and it caught the comet as a bright dot with a stubby little tail in images stacked over about a fortnight in late September and early October, from a distance of something like 230 million miles. Europa Clipper watched it. And this is my favourite category of these, so let me be clear about what Europa Clipper is. It is a very large, very expensive spacecraft that is on its way to Jupiter to find out whether the moon, Europa, has an ocean under its ice and whether that ocean might be habitable. It has a schedule, it has a decade-long cruise plan, and it got reprogrammed, mid-flight, to spend hours staring at a comet, and it managed ultraviolet observations at a moment when telescopes on Earth were blinded by the sun and simply could not. Psyche watched it. Psyche being en route to a metal asteroid. Another mission with somewhere to be. Another one that pulled over. Lucy watched it. Swift watched it. SOHO watched it. Tess, having already accidentally photographed it before anyone knew it existed, went back and did it properly on purpose. Hubble looked repeatedly. Spherex looked, in the infrared, more than once, and we're going to spend proper time with what Spherex found later because it's central to the whole story. And JUICE looked, which is the one with the best texture, so let me tell it. JUICE is Europe's Jupiter Icy Moons Explorer. At the time of the observation, it was in a part of its cruise where it was quite close to the sun, and the way you survive being close to the sun when you're built for Jupiter is you turn your big dish antenna toward the sun and hide behind it, which works beautifully. It also means your big dish antenna, the thing you talk to Earth with, is now pointing at the sun instead of at Earth. So JUICE took its observations while using its main antenna as a parasol, which meant it had to phone home through its little backup antenna instead, at a data rate that I can only describe as nostalgic. It was also on the far side of the sun. The team managed to pull down a quarter of one navigation camera image just to check the thing had worked, and it had. There was the comet, fuzzy and active. The rest of the data arrived in February 2026. 4 months. The observation sat on a spacecraft, complete for 4 months, waiting for the geometry to improve enough to send them home. I love that so much. We're all so used to information being instantaneous that there's something almost Victorian about a scientific result travelling by the equivalent of slow post, because the ship was pointing the wrong way. The ground-based stuff kept going long after the spacecraft had moved on too. The Very Large Telescope in Chile was still catching it in January and February 2026, well after most people had stopped paying attention, and it produced my favourite images of the whole campaign, sequences of about 14 minutes each, with the telescope tracking the comet, which means the comet sits still in the frame and everything else smears. All the background stars turn into little streaks, because they're the ones moving now, as far as the telescope is concerned. It's a complete inversion of how the sky is supposed to work, and it's a good visual reminder of how fast this thing was actually going. The stars couldn't keep up. Add it up and you get more than a dozen missions across at least 3 space agencies, plus essentially every serious ground-based observatory that could see it. The Very Large Telescope in Chile, the Nordic Optical Telescope, the Southern African Large Telescope, ALMA, Gemini, Subaru, Meerkat, Green Bank. Some of them repeatedly, over months. And what strikes me about the whole exercise isn't the hardware, it's the improvisation. None of this was planned. There was no interstellar object response program sitting in a drawer waiting for the alarm to go off. What there was several billion pounds worth of machinery scattered across the solar system doing other jobs, and a loose international community of people who all independently decided that this was worth interrupting those jobs for, and then wrote the emails and made the calls and got the approvals and repointed the telescopes in a matter of days for an object that would be gone before most grant cycles would have finished processing the paperwork. That's the bit worth sitting with. Not that we could do it, that we bothered. Now, since we're on the subject of instruments doing jobs they were never hired for, let's talk about the X-ray telescopes. Because one of the observations in that pile came from a satellite that has nothing to do with comets whatsoever, and it settled a question that had been sitting open since 1996. In 1996, a comet called Hyakutake came past, and it was a beauty, one of those ones that actually looked like a comet is supposed to look, hanging in the sky with a tail stretched halfway across it. And while everyone was enjoying that, somebody pointed an X-ray telescope at it. And I want to stress that this was not because anyone expected anything. It was a punt. We've got the time, why not observation, the astronomical equivalent of checking your coat pockets. The comet was glowing in X-rays, which made no sense. X-rays are the calling card of things that are violently energetic. The accretion disks around black holes, the coronas of stars, gas falling into things at a decent fraction of the speed of light. That's the X-ray sky. It's a catalogue of the universe's worst neighbourhoods. A comet is a dirty snowball a few kilometres across, sitting in the cold, minding its business. It has no business emitting anything, but there it was. The explanation took a while, and it turned out to be one of those mechanisms that's much better than the mystery was. It's called charge exchange, and the picture goes like this. The sun is constantly throwing off a thin wind of charged particles, the solar wind, and a fair fraction of what's in that wind is not just protons but heavier atoms that have been stripped almost bare. Oxygen with most of its electrons ripped away. Carbon in the same state. These are atoms that have been sitting in the sun's outer atmosphere at temperatures of 1,000,000-odd degrees, which is not an environment in which electrons stay attached to anything. So they come flying outward, hollowed out and desperate. Then they hit a comet's coma, which is a cloud of ordinary cool intact gas, water, carbon dioxide, whatever's boiling off, sitting there absolutely stuffed with electrons, and the stripped ion arriving at hundreds of kilometers a second grabs one, just plucks an electron straight off a passing water molecule, but it grabs it clumsily into a high energy level, and the electron immediately falls down to where it should be, and on the way down it throws off a photon, and because the ion is so severely stripped, the energy gap it's falling across is enormous, and the photon that comes out is an X-ray. So the comet isn't generating the X-rays exactly. The comet is a screen. The solar wind is the projector. The glow is what you see when a stream of very hot, very hungry ions runs into a cloud of very cold, very ordinary gas and starts stealing. I think that's a lovely bit of physics. The whole thing is a robbery, rendered in light. Anyway, once that was understood, it got confirmed at comet after comet, and it stopped being a mystery and became a tool. If you can see the X-rays, you're not really looking at the comet. You're looking at the interaction between the comet and the wind, which means you can learn about both. You can get at gas that other instruments struggle with. It's a genuinely useful diagnostic. And for 30 years, nobody could get it to work on an interstellar object. They tried. Of course they tried. Oumuamua. Nothing. Which, in fairness, Oumuamua wasn't producing a coma, so there was nothing for the wind to rob. The mechanism needs gas, and there wasn't any. But Borisov was a perfectly respectable comet with a perfectly respectable coma, and it still didn't yield an X-ray detection, and the reason was mundane and annoying. It was too far away and too faint, and there wasn't enough of it. So the question just sat there. Do interstellar comets glow in X-rays like ours do? Presumably. Probably. Physics is physics, and the solar wind doesn't check anybody's paperwork. But presumably is not a result. Nobody had ever seen it. Then came Survey Atlas, which was bigger, more active, and producing rather a lot of gas. The observation was made by XRSM, which is a Japanese-led X-ray satellite, JAXA, working with NASA and ESA. It ran from late on the 26th of November 2025 to the evening of the 28th, and the useful exposure came to about 17 hours. The instrument was X-TEND, which is the soft X-ray imager on board, and the field of view it was staring at covered a patch of space around 3 million kilometers across. Now, the timing of that looks arbitrary, and it wasn't, and this is the sort of constraint I find genuinely charming about doing astronomy with real hardware. XRISM is not allowed to look anywhere near the Sun. It physically cannot point within 60 degrees of it. Do that, and you cook the optics, and the mission is over. So the observing window wasn't chosen by anyone. It was chosen by geometry. The comet had gone round the Sun on the 29th of October, and it simply was not available to XRISM until it had swung far enough out from the glare to clear that 60-degree exclusion zone, and the moment it did, they went. A month after the most interesting part, because that was the first legal opportunity. 17 hours of staring, and there it was, a faint glow, extending about 400,000 kilometers out from the nucleus. 400,000 kilometers is more than the distance from here to the Moon. So the X-ray emitting region around this thing was wider than the Earth-Moon gap, produced by a lump of ice a couple of kilometers across. Which sounds mad until you remember that the glow isn't the comet, it's the cloud, and the cloud is enormous and thinner than any vacuum you could make in a laboratory. It's not a bright object. It's a vast, tenuous, barely there shimmer, and it took a dedicated satellite the better part of a day to gather enough photons to say so with a straight face. I should flag the caveat that the team themselves flagged, because they were careful about it, and I'd like to be too. The interpretation is that the glow comes from a diffuse cloud of gas surrounding the nucleus, which is what the charge exchange picture predicts and what everything else about the object supports. But they said in writing that it requires further analysis. 17 hours of a faint signal is not a lot of photons. They're confident, not certain, and the difference between those two words is most of what separates science from a press release. There's also a nice bit of context in how they showed the result. They plotted the comet's path against an all-sky X-ray map, the kind of thing built up by instruments that just stare at the whole sky continuously, like MAXI on the International Space Station or Eurosita's Deep Survey. And when you see it laid out that way, the scale of the exercise lands. The X-ray sky is this enormous mottled thing full of the brightest, angriest objects in the universe, and there's a little blue box on it, a tiny rectangle marking the patch where a satellite spent a day and a half looking at a snowball. Then ESA's XMM Newton went and looked as well in early December and got its own X-ray view. 2 independent telescopes, 2 independent images, same story. First interstellar comet ever seen in X-ray light. A 30-year question, closed. The result, when it came, was about as undramatic as results get. It looked completely normal. That's it. That's the result. The interstellar visitor interacts with our solar wind in fundamentally the same way as every comet from our own back garden. The stripped ions arrive, they steal electrons, the electrons fall, X-rays come out. No difference, no surprise. An object born around a star that died before the Earth existed, and it fits our physics without so much as a raised eyebrow. I love a null result, and this is a really good one, because it isn't actually null, it's a confirmation that the rules travel. The chemistry of this thing turned out to be genuinely strange, as we'll get to. Properly strange. Strange enough to make people rewrite their assumptions. But the physics wasn't strange at all. Same wind, same theft, same glow. There's also a practical dividend. We now know this works, which means the next one that comes through close enough and gassy enough gets an X-ray campaign as a matter of routine rather than as a gamble. That's how a field grows. Somebody proves the technique on one object, and then it's just a thing you do. Now, let's talk about what was inside it. The solar wind could only get at the outer cloud, which is material the comet had already let go of. The chemistry that mattered was still in there, and it took months to come out. In August 2025, 2 different infrared instruments went looking for methane and found nothing. That's where this bit starts, not with a discovery, with an absence. JWST looked, using its near-infrared spectrograph. Spherex looked, which is a NASA mission that surveys the whole sky in infrared and which had 72 dedicated pointings at this thing over 5 days in August. Between them, they had a solid look at what was coming off it. They found water ice. They found carbon dioxide. A lot of carbon dioxide, we'll come to that. They found the beginnings of carbon monoxide, no methane, nothing, not a whisper. And at the time, that was a shrug. Fine. Not every comet has methane in any detectable quantity. The object was still a long way out, come back later. Then, in December, they came back later. JWST turned its mid-infrared instrument on it, MIRI, on the 15th and 16th of December 2025, when the comet was 220 astronomical units from the Sun, which, incidentally, went slightly wrong. 2 of the observations failed to lock onto a guide star, so the telescope couldn't point precisely enough, and those had to be repeated on the 27th, by which point it had drifted out to 254 AU, which sounds like a nuisance and turned out to be a gift, because it accidentally gave them 2 epochs 12 days apart instead of 1, and the difference between those 2 epochs is where the story is. Methane. Loud, clear, unmistakable, at 7.6 micrometers. First time it had ever been detected on an interstellar object. The team was led by Matthew Belyakoff at Caltech with Ian Wong at the Space Telescope Science Institute, and it went into the Astrophysical Journal letters, and it was the first mid-infrared chemical fingerprint anybody has ever taken of anything from another star, and it wasn't a trace. On the 15th and 16th, the methane was coming off at about 13.7% of the rate the water was. 12 days later, on the 27th, it was 27%. It doubled, relative to water, in under a fortnight on the way out, as it was getting colder. That is not how a comet is supposed to behave, and to see why, you need one idea, and I'm going to explain it once, properly, and then never again. A comet is not a uniform snowball. Think of it as layered, not neatly, not like a cake, but layered in the sense that the outside has had a very different life to the inside. The outside of this object had been sitting in interstellar space for an unimaginably long time, exposed. Cosmic rays, ultraviolet from every star it drifted past, the slow, patient grind of radiation. And radiation does 2 things to ice. It cooks the volatile stuff out of the top layer over time, and it chemically transforms what's left, turning simple organics into darker, heavier, tarrier compounds. That's the red colour. That's the crust. So the surface is not a sample of the comet. The surface is a scab, and beneath the scab, shielded, is everything that hasn't been touched. The stuff that was there when the thing formed. Which, in this case, means ices that had never once been warm. Now bring it toward a star. Heat lands on the outside and starts working inward, and this is the part people's intuition gets wrong. It's slow. Ice is a poor conductor. A dark, tarry, porous crust is a worse one. The heat has to physically diffuse down through the layers, and that takes time, not seconds, not days, months, which means the comet's closest approach to the Sun and the comet's most vigorous outgassing are not the same event. There's a lag. The Sun stops pushing heat in, and the heat carries on going down, the way a roast keeps cooking after you take it out of the oven. 3I Atlas went round the Sun on the 29th of October. The methane showed up in December. The heat had finally reached a layer it had never reached before, and the methane that had been locked in there since the thing formed started coming out. That's the whole mechanism. That's the eruption. It is not a rupture, it's not an explosion, and nothing came apart. The comet survived its solar passage entirely intact, which is worth saying plainly, because a fair number of people were expecting it to break up and it flatly didn't. It's a thermal lag. It's a delayed release from under a crust. It's the least dramatic possible explanation, and it accounts for everything. There's a second factor stacking on top, and it's neat. In our solar system, there's something called the water ice line, at roughly 2.5 AU. Inside it, water ice sublimates readily. Outside it, water ice largely stops bothering. And in December, 3I Atlas was crossing exactly that boundary. 220, then 254. So the water was switching off, and methane, which is far more volatile and needs far less heat, was still fully switched on, which means part of that jump from 13.7 to 27% isn't methane increasing at all, it's water leaving. The ratio moved because the denominator collapsed. As Belyakov's team put it, water production from the coldest regions was shutting down, while methane and carbon dioxide stayed fully activated. And in fact, if you look at the absolute numbers rather than the ratio, it's even clearer. The methane itself was coming off at about 4.2 times 10 to the 26 molecules per second in the middle of December, and by the 27th that had dropped to 2.3 times 10 to the 26. So the methane didn't double, the methane nearly halved. Everything was winding down as it got further out exactly as it should. The whole object was quietening. It's just that the water was quietening faster, which is a good reminder about ratios generally. Half the time when a ratio does something startling, the interesting thing happened to the bottom of the fraction. SphereX was watching this too, and its December numbers are worth having. Water production had climbed to something like 1.4 times 10 to the 28 molecules per second. Carbon monoxide was running at 55% of the water rate, carbon dioxide at 23%, and a broad organic signature at 14%. That last one showed up as a wide bump in the spectrum around 3.2 to 3.4 micrometers. Not a clean single line, a smear, which is what a mess of carbon-hydrogen bonds looks like when you can't resolve which molecules they belong to. Methanol was in there. Cyanide. The general chemical soup. There's a nice structural detail in the MIRI images too, and it tells you something about where things are coming from. The water vapour was spread out enormously, far beyond the nucleus, filling the whole coma, while the carbon dioxide and the methane were concentrated tightly enclosed. That's because they've got different sources. The methane and the carbon dioxide are coming straight off the solid body, so they're densest where the body is. The water is largely coming off icy grains, little chips of ice that got thrown off the nucleus and are drifting outward in a cloud, each one slowly sublimating as it goes. So the water is being produced everywhere the grains are, which is a volume the size of a planet. Carbon dioxide in particular built up into something ridiculous. At one point, the carbon dioxide coma was measured at something like 700,000 kilometers across. The comet was, functionally, wearing a fog bank several times wider than any planet in the solar system. And the carbon dioxide deserves its own moment, because it was strange from the very beginning. The ratio of carbon dioxide to water measured back in August came out at 7.6, and that number sits 4.5 standard deviations off the trend line for long-period and Jupiter family comets. 4.5 sigma, that's not a bit high, that's a different population. The same spectra also picked up nickel, in gas form, at 7,507 micrometers, which is peculiar, and I'll come back to it, because it's one of the details that's kept a certain argument alive. So the picture that emerges is of an object that is genuinely quantitatively unlike ours. Far more carbon dioxide than it should have, far more methane than it should have, and it took months of solar heating to admit to any of it. Now, one thing that bothers me, and it bothers the researchers too, and I'd rather tell you about it than tidy it away. Carbon monoxide is more volatile than methane. It needs even less warmth to boil off. So if the story is, the volatile stuff got baked out of the crust and only the buried layers still have it, then carbon monoxide should have been the last thing to appear, not one of the first. It should have been more depleted from the surface than methane, not less. It showed up early. Methane showed up late. That's backwards, and nobody has a clean answer for it. I find that reassuring in a way. Not everything resolved. There's a real, specific, unglamorous puzzle sitting in the middle of this dataset, and it's the kind of thing that'll get argued about in papers for years, and probably eventually turn out to be something about how the ices are physically mixed rather than layered. But talking a bit about the water now, rather than the methane, because there's an entirely separate measurement hiding in it, and it comes down to counting neutrons. Hydrogen is the simplest thing there is. 1 proton, 1 electron. That's the whole atom. It's the first entry in the periodic table because there is nothing simpler to put in front of it. But there's a variant. Take that hydrogen atom and put a neutron in the nucleus alongside the proton. It's still hydrogen. Chemically it behaves the same, it bonds the same, it does all the same things, but it now weighs twice as much. That's deuterium, heavy hydrogen. And because water is 2 hydrogens and an oxygen, you can have water with a deuterium in it instead of an ordinary hydrogen. Heavy water. It's real water. You could drink it. It's not poisonous in small amounts. It just weighs about 10% more than it ought to, and it tastes very slightly sweet, which is a fact I've never known what to do with. Deuterium exists in tiny quantities everywhere. Roughly 1 hydrogen atom in every 6 or 7,000 in the universe is deuterium, and that ratio, deuterium to ordinary hydrogen, written DH, is the single most useful number in this entire story because of one property. It records temperature. Here's why, and it's genuinely elegant. Chemical reactions in space don't care much about mass, but they care a lot about energy. And a deuterium atom, being heavier, sits slightly lower in an energy well than an ordinary hydrogen does. It's harder to knock out. It's stickier. So imagine a molecular cloud, cold gas and dust, drifting, with grains of dust in it that have thin films of ice on their surfaces. Chemistry happens on those grains. Atoms land, wander about, bump into each other, form molecules. And in that process, when there's a choice between grabbing an ordinary hydrogen and grabbing a deuterium, the deuterium wins slightly more often than its abundance says it should. Not by much, but it wins. And the colder it is, the more it wins, because at higher temperatures there's enough energy sloshing around that the difference stops mattering. Everything gets knocked loose, the reactions run both ways, and the preference washes out. At very low temperatures there's no energy to spare. The reactions only run one way, and the preference accumulates. Every single reaction, over millions of years, quietly stacking deuterium into the ice. So a cold place makes heavy water, a very cold place makes very heavy water, and once it's made, if nothing ever warms it up again, it stays made. Warm it, even gently, even for a while. And the chemistry starts running backwards and the signal degrades, which means the D-et ratio in a comet's water is a thermometer that was switched on when the comet formed and has been switched off ever since. It doesn't tell you what temperature the comet is now. It tells you the temperature of the place where its water was assembled billions of years ago, preserved because nothing has been warm enough since to erase it. For our own comets, this has been measured many times. Halley, Hale-Bopp, Hyakutake, and 67P, which is the gold standard, and which deserves a sentence of its own. 6SP Churyumov-Gerasimenko is the comet Europe flew Rosetta to in 2014, a rubber duck-shaped lump of ice about 4 kilometers across that a spacecraft chased for 10 years, caught, and then flew alongside for 2 more, all the way into the sun and back out. We put a lander on it. Badly as it turned out, Philae bounced and ended up wedged in a crack in the shade, which is one of the more heartbreaking small failures in the history of the field. But Rosetta itself worked beautifully, and it sat next to that comet with a mass spectrometer sniffing the gas for 2 solid years, which means that for 67P we don't have a ratio derived from a spectrum taken across the solar system. We have measurements taken from about 10 kilometers away, repeatedly in situ. It is the best characterized comet that will likely ever exist, and it's the yardstick everything else gets held against. The numbers cluster in a range, and that range corresponds to formation somewhere in the outer solar system. Cold, but the kind of cold you get a few billion kilometers from a perfectly ordinary star. Earth's oceans sit lower still. Now. On the 22nd of June 2026, a paper went into Nature. The team was led by Martin Cordner at NASA's Goddard Space Flight Center, with Nathan Roth and Marco Micheli, and a long list of others, and the title was about as unambiguous as scientific titles get. Isotopic Evidence for a Cold and Distant Origin. They'd got the observation back in December, when the comet was freshly warmed and its ancient ice had turned into a bright coma of gas, which is the only time you can do this. You cannot measure the ice. You can only measure the ice after it has stopped being ice. So they'd needed the object to be hot enough to be steaming and close enough to be bright, and that window was narrow, and they interrupted JWST's schedule to get inside it. And the way you actually do the measurement is worth a minute because it's not obvious. You're not counting atoms. You can't. What you're doing is looking at light. Every molecule vibrates and rotates at very specific frequencies, determined by the masses of the bits it's made of and the stiffness of the bonds between them. It's a tuning fork, effectively, and it will only ring at its own notes. So when infrared light passes through or comes out of a gas, that gas prints its notes onto the spectrum. Now swap one hydrogen in a water molecule for a deuterium. The bond is the same, the chemistry is the same, but one end of the tuning fork just got twice as heavy, so all the notes shift. Not by much, but by a precise calculable amount, to frequencies that ordinary water doesn't touch. So heavy water has its own signature, sitting slightly to one side of normal waters, and if your instrument is sensitive enough, and its resolution is fine enough, you can see both sets of lines at once, in the same spectrum, and compare how strong one is against the other. That's the measurement. You're weighing an isotope ratio in a cloud of gas hundreds of millions of kilometers away by looking at where the light dips. There are perhaps 2 instruments in existence that can do that on an object this faint, which is why the schedule got interrupted. The number came back at 0.98%, give or take 0.06, about 30 times higher than any comet from our solar system. 30 times, not 30% higher, 30 times. And when you feed that back through the chemistry, it implies formation somewhere colder than about minus 243 degrees Celsius. I want to be careful about how I put this, because very cold is a phrase that has been drained of all meaning by overuse. So, absolute zero is minus 273. The empty space between galaxies, warmed by nothing but the leftover heat of the Big Bang itself, sits at about minus 270. The surface of Pluto, the coldest properly familiar place, the thing we point at when we want to say cold, is around minus 230. Minus 243 is colder than Pluto, by a comfortable margin, and that's an upper limit. It's the warmest it could have been. There is nowhere in our solar system like that. There never was. Even the Oort cloud out at the ragged edge of the sun's influence is warmer, because the sun is still technically shining on it. To get that cold, you need to be genuinely far from any star, or in a place where the star hasn't got going yet, or both, sitting inside a dense, dark, insulating cloud where starlight simply doesn't reach. That's where this thing's water was made, not merely far out, somewhere with effectively no sun at all. And there's a second measurement I like even more, because it's stranger. Somebody went back to the same JWST data and pulled out the deuterium in the methane. You can do this because a methane molecule with a deuterium in it has a slightly different spectral signature, and if your data's good enough you can count them separately. The DH in the methane came out at 331%. That's 14 times the value measured in Comet 67P, which is the comet we have the best data on in the whole catalogue, because we sent Rosetta there and parked next to it for 2 years. 14 times. Fine. Consistent with everything else. This thing is deuterium rich across the board. But then they did something cleverer. They asked, within a single comet, how does the methane's deuterium compare to the water's deuterium? Rosetta had answered that for 67P. The methane was about 4.8 times more deuterated than the water. For Three's Atlas, the same figure came out at 3.5. Those two numbers agree to within about 1 and a bit standard deviations, which is to say, they agree. Sit with that for a second. Two objects with nothing whatsoever in common. One formed around our sun 4.5 billion years ago. One formed around a star that no longer exists, in a colder place, at a different epoch of the universe. Their absolute deuterium levels differ by a factor of 14. And the relationship between how deuterated their methane is and how deuterated their water is, that's the same, which means whatever process puts deuterium into methane preferentially over water isn't a local quirk. It's not something about our sun or our disk or our particular corner. It's a mechanism, and it ran the same way here and it ran the same way there, across 14-fold differences in outcome and billions of years of separation. I find that quietly astonishing. The chemistry is portable. You could take our chemistry textbooks to a star that died before the Earth had a surface, and they'd still work. Now let's talk about the carbon in that same dataset, because that's where the age estimate comes from. Think of the galaxy as a riverbed, and heavy elements as silt. At the very beginning, right after the Big Bang, the universe was hydrogen and helium, and a trace of lithium and essentially nothing else. No carbon, no oxygen, no iron. Nothing you could build a planet out of, let alone a person. The whole periodic table below the first few entries simply did not exist yet, because nothing had made it. Stars made it. That's the only source. Stars fuse light elements into heavier ones in their cores, and then at the end of their lives they either shed those layers gently or blow themselves apart violently, and either way the material goes back out into the gas between the stars, which then collapses and makes new stars which do it again and again, and each generation leaves the gas a little richer than it found it. So the interstellar medium accumulates, it silts up, and the further along in cosmic history you are, the more heavy elements are lying about in the gas, and the more of them end up in whatever forms next. Astronomers call the general level of this metallicity, using a definition of metal so aggressive it includes oxygen and carbon, which annoys chemists and I think is quite funny. Now carbon specifically. Carbon comes in two stable flavours, carbon-12 with 6 protons and 6 neutrons, and carbon-13 with an extra neutron. Carbon-12 is far more common, but the ratio between them isn't fixed, because the two are made by different processes in different kinds of stars on different timescales. Broadly, and I am simplifying, but the direction is right, Carbon-12 gets pumped out early and fast by massive stars that live briefly and die spectacularly. Carbon-13 comes disproportionately from a slower route, from lower mass stars going through their late life phases, which takes a lot longer to get going and keeps topping up for billions of years afterwards. So carbon-13 builds up over time, late, gradually. The early universe was carbon-13 poor. The universe now is comparatively carbon-13 rich, because there's been a great deal more time for the slow contributors to do their bit, which turns the carbon isotope ratio into a clock. Not a precise one. It's a sedimentary clock, it tells you roughly which layer you're in, but a clock. Our Sun formed 4.5 billion years ago, which in the galaxy's 9 or 10 billion year run of star formation is recent. We're late arrivals, so our system is comparatively well silted. There's plenty of carbon-13 in everything around here. JWST measured 3I Atlas. The ratio of carbon-12 to carbon-13 came out between 141 and 191 in the carbon dioxide, and between 123 and 152 in the carbon monoxide. Higher numbers on that scale mean less carbon-13. It's a fraction with carbon-13 on the bottom, so as the carbon-13 dwindles, the number climbs. And those values are above what we see in the solar system. They're also above what we see in nearby molecular clouds, and above what we see in protoplanetary disks, which is to say, above the raw material that stars are being built out of right now, today, elsewhere in the galaxy. There's barely any carbon-13 in this thing, which means it was assembled before there was much carbon-13 to assemble it out of. It's from a lower layer of the riverbed, a primitive, metal-poor environment, the kind you got when the galaxy was young and the silt hadn't built up. Put that together with the deuterium, cold, unbelievably cold, and run it through models of how the galaxy's chemistry has evolved over time, and you get a number. 10 to 12 billion years. That's when this thing formed. Give or take with all the caveats I'm about to give you, but that's the range. Let me put that in some order, because these figures get thrown around until they stop registering. The universe is about 13.8 billion years old. So 12 billion years ago, the universe was under 2 billion years old. It was an infant. Our Sun would not begin to exist for another 7.5 billion years. The Earth, obviously, nothing. The galaxy itself was a very different object. Smaller, messier, still assembling, still merging with things. And it was making stars at a furious rate. That era has a name, cosmic noon. It's the peak of star formation in the universe's history, the point at which the galaxies were converting gas into stars faster than at any time before or since. The lights were all coming on at once. 3I Atlas formed then, in a cold, dense cloud, around a star that was itself brand new, in a galaxy that had barely started. And that star is dead. It has to be. 10 to 12 billion years is longer than most stars get. Whatever it was, it lived its life and it ended, puffed off its outer layers and shrank to a white dwarf, or went out in something louder. And it did so long before there was anything on Earth to have an opinion about it. Probably before there was an Earth. The comet doesn't know. The comet got thrown out at some point by some gravitational interaction, a passing star, a planet in the system, something that gave it a shove it couldn't recover from, and it went off into the dark carrying a chemical snapshot of its birthplace, and it has been carrying it ever since, unchanged, because nothing out there was ever warm enough to change it. And then, after all that time, it fell past our star, warmed up for a few months and told us. Cordiner put it about as well as it can be put. He described it as a unique opportunity to study an ancient object from the distant galaxy, probably predating our Sun and solar system, and said that on the one hand you get direct insight into that distant time and place, and on the other you learn something about how unusual our own solar system might be. That second half is the part I keep chewing on. We've had exactly one example of a planetary system's chemistry, examined in detail, forever, ours. And when you've got one of something, you can't tell whether it's typical or bizarre, because there's nothing to compare it to. This was the first real second data point, and it came back different, properly different, not marginally. There's an implication buried in the metal-poor bit that I think is the most interesting thing in this whole module, and it's easy to skate past. Planets are made of silt. That's the crude version, but it's true. Rocky planets are essentially a pile of the heavy elements that stars manufactured, and you can't build one out of hydrogen. So the standard expectation has always been that early, metal-poor systems shouldn't have made much solid material. There simply wasn't the stock. You'd expect thin disks, small bodies, not much to work with. It's one of the reasons people generally assume the galaxy's rocky planets are a relatively late development, and here's a 2.5-kilometre lump of ice and organics that was assembled in exactly that kind of environment and got ejected from it, which means the system it came from had enough material to build things and enough going on gravitationally to throw them out. That's a system with structure. Something in there was massive enough to fling a comet into the void, and something made the comet in the first place. Which is a data point about a period of galactic history that we have essentially no other physical samples from, and it says there was more happening out there, earlier than the simple version would suggest. Now. The caveats, because I'd be doing you a disservice. That 10 to 12 billion year figure is not a birth certificate. It's an inference, and it depends on models. Specifically, models of how the galaxy's chemical composition has changed over time, which are decent models, but which are models. If those are wrong in some systematic way, the number moves. It's a range, not a date, and it's a range with real machinery behind it, rather than a measurement you could hold up. What I'd say is, the deuterium and the carbon are two independent lines of evidence, measured from different molecules pointing the same direction, cold and old and poor in the elements that came later. They didn't have to agree, they did. And there's a third line, from a completely different telescope. Cyrielle Aupetom at the University of Edinburgh led a team using the Very Large Telescope in Chile, and they went at it from another angle entirely. Cyanide. One carbon, one nitrogen, bonded together, and it's one of the easier things to spot in a comet from the ground. They pulled the carbon and nitrogen isotopes out of it, in visible light, from a mountain, while JWST was doing its infrared work from 1.5 million kilometers away. Same conclusion. That's what makes this stick, for me. Not any single measurement. The fact that 3 separate groups, using 3 different techniques on 3 different molecules, walked in with different instruments and walked out with the same answer. And that brings us to the aliens, which we should probably deal with properly. So, obviously a lot of people thought it was a spaceship. I want to handle this properly rather than sneering at it. Because sneering at it is both lazy and a bit unfair. The idea didn't come from nowhere, and it isn't only coming from the usual corners of the internet. It's also coming from a tenured astrophysicist at Harvard, and while I think he's wrong, I don't think he's a fool, and the argument is worth laying out honestly before we take it apart. Avi Loeb has been making the case for years, since Oumuamua, and with 3i Atlas he compiled a running list of what he called anomalies, and some of them are real observations. Let me give you the strongest ones. The trajectory came in within about 5 degrees of the plane the planets orbit in, and as I mentioned earlier, that's a coincidence with maybe a 1 in 500 chance, given that the galaxy's disk is tilted roughly 60 degrees away from ours. If you're arriving from a random direction, you shouldn't land in our lane. The timing put it close to Mars and then close to Jupiter, and hid it behind the Sun at exactly the moment we most wanted to look. The gas around it, before perihelion, had much more nickel in it than iron, which is a genuinely odd ratio, because nickel and iron normally travel together in space, and the proportion is closer to what you'd find in industrially produced nickel alloys than in a rock. And when you process the Hubble images with a filter that strips away the smooth glow of the coma, you can see jets, and there's a set of 3 little ones, arranged about 120 degrees apart from each other, symmetrically. That's the case, or the strongest version of it anyway. And I'll say this much for it. Written out in a list like that, it has a certain momentum. The individual answers are fairly ordinary though. Start with the symmetric jets, because that's the one that grabs people. A regular geometric pattern feels like design. Nothing natural is neat, so neat means made. That's the instinct. But rotating bodies produce regular patterns constantly without anyone's help. The comet is spinning, on a fixed axis, at a fixed rate. Sunlight sweeps across its surface in a cycle. If there are particular patches where volatile ice sits close to the surface, each one lights up when it rotates into the sun and shuts down when it rotates out. The geometry of the spin imposes the rhythm. You get jets at regular angular intervals, not because someone placed thrusters there, but because a spinning object has regular angular intervals by definition, and anything driven by that spin inherits them. Snowflakes are 6-fold symmetric and nobody carves them, the trajectory alignment, someone had to draw that card. We've got 3 interstellar objects. If none of them had ever come in near our plane, that would also be a coincidence, and nobody would remark on it. This is the difficulty with anomaly hunting generally. If you list enough properties of any object, some of them will be unlikely, because most properties of most things are unlikely. The trick is that the unlikeliness has to be specified before you look, not after. The nickel is interesting, and I don't want to dismiss it. It's a real result and it needs explaining, and there's work suggesting nickel can come off in a compound form at low temperatures that iron doesn't do. That's an open bit of chemistry. Open bits of chemistry are not evidence of engineering. They're evidence that comets are complicated. There's also a set of claims that circulated widely, that the thing dramatically spun up, that it fragmented, that it did various energetic things, which trace back to blog posts rather than to papers, and which I'm not going to repeat as fact because the peer-reviewed record says it survived its solar passage completely intact. But look, all of that is arguing. Arguing is cheap. Somebody went and checked. On the 18th of December 2025, the day before its closest approach to us, the Green Bank telescope was pointed at it. Green Bank is the largest fully steerable radio telescope on Earth, 100 meters of dish sitting in a valley in West Virginia inside a legally enforced radio quiet zone, and it listened across a range from 1 to 12 gigahertz. That's the Breakthrough Listen program, and the logic is straightforward. If you were an interstellar probe and you wanted to talk to anyone, you'd almost certainly do it with narrowband radio, because narrowband radio is cheap to produce, easy to spot, and passes through interstellar space without getting absorbed, nothing. Meerkat in South Africa listened too, with a technosignature search running on the data in parallel with the actual astronomy. It detected hydroxyl, which is exactly what you'd expect. That's what sunlight does to water. It breaks it apart and the fragments glow at radio frequencies. Perfectly ordinary comet chemistry, and no artificial signal down to a limit of 0.17 watts across the 900 to 1670 megahertz band. I want to dwell on that number because it's the best number in this entire section, 0.17 watts, at that distance. That is roughly the transmitting power of a mobile phone. If there had been a handset sitting on that comet, switched on, chatting away, we would have heard it. Then the Allen Telescope Array had a go, in a study led by Sophia Sheikh that came out in the Astronomical Journal, and this is the one I find most human. They ran the search. It threw up candidate signals, a whole pile of them, and then every single one was traced back to something on the surface of the Earth, or to one of our own satellites in orbit. We keep finding ourselves. That's the recurring comedy of the whole discipline. You point the most sensitive listening equipment ever built at the sky, and the sky is so full of our own noise that the first 100 things you find are always a mobile mast or a badly shielded satellite downlink or, on one legendary occasion at a different observatory, a microwave oven in the staff kitchen. 9 of them, in one of the searches, showed up when the telescope wasn't even pointing at the target, which is the giveaway, and which is exactly why you do the check. If the signal's still there when you look away, the signal isn't from where you were looking. So, nothing, from several instruments, at different frequencies, run by different teams. The most sensitive radio observations ever made of an interstellar object, and the conclusion of every one of them was the same. There's no evidence it's anything other than a natural object, and everything about its behaviour and composition is what you'd expect from a comet. An unusual comet, a chemically strange comet, but a comet, which I think is a better outcome than the alternative, honestly, and I'll explain what I mean. If it had been a probe, we'd have learned that somebody else is out there. Enormous, obviously, but we'd have learned it about them. What we got instead is a sample, an actual physical sample of the material a planetary system was built out of 10 or 12 billion years ago in conditions nothing here has ever experienced, delivered to our door for the cost of a few repointed telescopes. We could never have gone and fetched it. Even if we started building an interstellar probe today, with everything we've got, we couldn't reach a system like that, and if we could, the system isn't there anymore. So it's mostly luck is what it is. It came past and we happened to be looking. People did ask, of course, whether we could chase it. Send something after it, get close, take a proper look. And the answer is a flat no, and the reason is that number from earlier, the residual speed. That's what you'd have to match, and then exceed from a standing start, having launched from a planet that's going the wrong way round relative to it. Voyager 1, which is the fastest thing we've ever thrown out of the solar system, and which has had decades and multiple planetary slingshots to build up speed, is doing about 17 kilometers per second. This thing does more than 3 times that, permanently, without trying, and you'd have to build the spacecraft and get the funding and launch it, all inside the few months between we've spotted something and it's leaving, which is not how spacecraft happen. The gap between noticing an interstellar object and losing it is shorter than the gap between proposing a mission and getting the first meeting in the diary. So the observing campaign wasn't a preliminary, it was the whole thing. That was our shot, and it won't be the last. The Vera Rubin Observatory has now started its survey, a telescope in Chile with a camera the size of a small car, designed to photograph the entire visible sky every few nights, over and over, for 10 years. And the thing that makes it matter here is that it is fundamentally the same trick Atlas does, just done with an absurdly bigger mirror and an absurdly better camera. Photograph. Photograph again. Ask what moved. Rubin had already photographed 3i Atlas, as it happens during its commissioning phase, before it was properly switched on, which is becoming a theme with this object. It kept turning up in data belonging to instruments that weren't looking for it. The expectation is that Rubin will find these things regularly, not once a decade, regularly. The estimate is that the solar system probably has interstellar objects passing through it, more or less continuously, and always has, and the only reason we've caught 3 is that we've only recently built anything capable of noticing. And I think the honest reason we've only got 3 isn't that they're rare, it's that they're faint and small and fast, and they don't announce themselves. Everything about an interstellar object is designed, if that's the word, and it isn't, to slip past a survey that's optimized for something else. Atlas is looking for things that might hit us, which means things on our sort of orbits, at our sort of speeds. Something arriving perpendicular to expectations at that kind of speed is precisely the kind of thing a system like that is worst at. Rubin doesn't have that problem, because Rubin isn't looking for anything in particular. It's looking at everything, all the time, and letting the software sort it out afterward, which is a fundamentally different philosophy. You stop hunting and you start recording, and then you go through the recording later, at leisure, and find what you weren't smart enough to look for. Given how much of tonight's story has been about people digging useful things out of archives that already had them, that seems like the right lesson to have learned. Which reframes the whole story, really. This wasn't a visitation. There was no arrival. The traffic has been going past the window for 4.5 billion years, and we've just now got the eyes to see it. I've got a whole video coming on Oumuamua, incidentally, because that one is genuinely unresolved in a way this one simply isn't, and it deserves the time. As of tonight, it's out past Jupiter and going. It crossed Jupiter's orbit back in March, and it's been climbing away ever since, slowing very slightly as the Sun tugs at its heels, which the Sun will lose, as we established, and lose comprehensively. By the early 2030s, it'll be clear of the planetary region entirely, and after that there's just the long quiet again, indefinitely, with 58 kilometers per second in the bank and nowhere in particular to be. The instruments that could see it have mostly given up. It's too faint now. The data isn't going anywhere, though, and that's the part that carries on. There are people who will spend the next decade working through what was collected in those 18 months, and some of the best results probably haven't been written yet. Stephanie Milam, who worked on the web paper, said something about all this that I keep going back to. She said that finding rare isotopes is fascinating for scientists, but the bigger picture is the possibility of prebiotic chemistry elsewhere in the galaxy, that we know of exactly one place in the whole cosmos where the chemical ingredients led to life, and that studying objects like this is a real step toward finding out how common, or how uncommon, those conditions are, and that's what was in it. Methanol, formaldehyde, cyanide, organics, not life. Nobody has suggested that, and I'm not going to, but the ordinary starting materials, the stuff you'd want on hand, made in the cold and the dark, around a star that was gone before the Earth had a crust and carried here intact. What I find I've landed on, after all these months of reading, is that the least interesting question about this object turned out to be the one everyone asked first. Whether it was alien. It wasn't, and we checked properly, and that's fine. The interesting question was the one nobody thinks to ask, which is whether our solar system is normal, And the answer, on a sample size of 2, appears to be not especially. The conditions that made this place aren't the conditions that made that place, and the chemistry that came out of the two is different enough that you couldn't mistake one for the other. I keep thinking about those pre-discovery images, though. May 2025, sitting on a planet-hunting satellite, months before anyone knew. It was in our data before it was in our news, and now it's back to being data, a few terabytes on some drives, which will outlast the object's visibility by a very long way, and which will still be there when someone in 40 years goes rummaging for a comparison with whatever comes past next. Which something will. Probably sooner than we'd have guessed a couple of years ago. Anyway, that's 3i Atlas. Sleep well.